thank you all for having me. And I'll just briefly mention that I hope we could all, this relationship continues for a long time if a AI Institute grant gets funded. But today I'm going to talk about development and assessment of a quantum genomic classifier, and we'll just dive in. So first, here's a brief outline. I'm going to talk about a classical version of our genomic classifier. I'll give a brief introduction to quantum mechanics, as I assume not everybody is steeped in that. And then I'll give a brief introduction to quantum computing. And then I'll go over the quantum genomic classifier, including kind of a schematic general algorithm, implementation on a IBM 5-qubit and 14-qubit quantum computers. And then I'll go over our results, some conclusions, challenges, there are plenty, and some opportunities. All right. So first, a classical version of our classifier is as follows. So we're just going to split the genome into sections, which we commonly do anyways often. And just kind of very abstractly, so here I show 8 regions, and abstractly, if there's some genetic mutation or alteration that we detect, I'm going to give a sample a value of 1 in that region. And if there's nothing anomalous detected, I'll give it a 0, okay? And we're going to have control and disease cases. So think of like a disease control cohort. This was actually inspired by a control schizophrenic cohort, but I'll just keep it kind of abstract at this level. And I'll even get into why that is the case too. So here I have a control vector where in the first 4 regions I have some genomic aberration, and in the last 4 I don't. And then in the disease, this is well separated. The first 4 don't, and the last 4 do have an aberration. Now here's my sample, and if I have a classifier, I'd like to classify it. So especially for students, does anyone want to take a shot at answering whether or not this is, do you believe this disease or control? Anyone want to take a stab at it? Given the pattern, what it's more like?
We have a comment that said it was disease.
Very good. And I can't access the comments because I got the laser pointer. So just feel free to interrupt me. Anyways, thank you. So that, so it's going to be disease. And so that's the correct answer. And we know one way that we could easily have gotten this answer algorithmically, and I'll formalize this in a second, is by calculating the dot product between the test sample and the control vector, as well as the test sample and the disease vector, and assessing which dot product was greater. So if you just look, the dot product for the control times the control vector and the test, it comes out to 1. And the dot product between the disease and the test comes out to 3. Its dot product is greater, so we can classify it as disease. Now, using a simple dot product classifier can only be done with highly separable data. That's what I'm going to be talking about today. But I'll also at the very end describe how we can maybe build classifiers that are more complicated and powerful. All right, so here's now, in more formal mathematical language, just slightly more formal, what this classifier does in kind of a simple algorithm. If the dot product between the control and the test is greater than the dot product between the disease and the test, then I'm going to classify the test as control. And then otherwise, if the disease is greater, the dot product with disease and test is greater than the control, then it's disease. And with this classifier, I can get into a situation where data is the test is unclassifiable. That's when the test is exactly equidistant between the disease and the control. And even if it's very close within noise, it won't be classifiable robustly. Okay, so let me just ask now, how many operations does it take to calculate the dot product for n regions? Well, By my counting, it's n multiplications and n minus 1 additions simply. So that's an order n method, order n operations. Okay. Now I'm going to add another layer which primes the pump for the quantum classifier. Now, normally when you define these regions, you number them: region 1, region 2, region 3, etc., up to 8. Okay, but I'm going to use a binary way to encode these regions. So 0, 0, 0 is going to be region 1, 0, 0, 1 is going to be region 2, 0, 1, 0 is going to be region 3, and so on. Okay, and you can relate this, the region, in terms of the regular 1 through 8 alphanumeric number through the binary scheme using this little formula where the F3, F2, F1, each F takes the value of 0 or 1. And so using the scheme, for example, if we look at region 2, we have, that's a 1, 0, 0. Let me just check my formula. I have 1 plus 1 times 2 to the 0, which is 1. The other 2 are 0, so that's 2. And you can check that this binary encoding works. And you'll see why I'm doing this now. Any questions? I'm happy to take questions along the way too. All right, excellent. So what about multiple samples? Maybe I've showed you what one sample does. Let me just show you generally, and you guys have probably seen formulas like this for simple linear kernel classifiers. If I have multiple samples, then I can more formally mathematically define this kind of classifier as the predicted class label, which can take a, let's say in this case now, a 1 or a minus 1, is equal to the sign of the sum over all the samples of each sample's training class, which is 1 for disease and minus 1 for control. It's that particular sample's disease vector or control vector, dot product, and taking the dot product with tests. So here I'm just taking the sum of dot products, okay, and multiplying it by its class value. Now, if I just separate out by classes, I take all the terms with disease plus 1 and control minus 1, I can separate this sum out, and this is the sum over disease samples and the sum over control. But because it's linear and because the test does not involve the index, I can separate it out. And so this becomes a sum over all the disease vectors, which I call D superscript 0, as well as all the control vectors, superscript 1, and it's just the difference between those pre-summed vectors where I take the dot product of each and I can perform the classification. This is important because we take advantage of this with the quantum computer. Quantum computer does some things very well and some things very badly. And for example, you'd have to come up with an algorithm to even sum vectors, which is not necessarily a simple thing to do. Any questions? And then here's just this drawing just shows you that we have a simple kind of linear classifier with some simple plane that separates the classes, but we're going to ultimately sum each of the sets, each of the samples class vectors into one big class vector for class A, say, and another one for class B, which is in our case disease and control. All right. So now I'm going to turn to quantum mechanics. All right.
Ask a quick question. So
yeah, absolutely.
We've illustrated these as 2D, but in reality, they're higher dimensional. They're high dimensional, right?
That's correct. That's correct. That's excellent. Thank you for that. Yes. So in fact, the advantage ultimately of using this for a quantum computer would be extremely high dimension. So in principle, what I'd like to think about, and where we could even maybe get to with an actual once we get quantum computers working very powerfully, the human genome is 3 billion letters, and I would like to execute this on nearly the 3 billion letters, for example. So yes, much higher dimension. So that's correct. Does that address the question? Well, okay, I hope it does.
Yes, thank you. Sorry, I had it muted.
No, it's okay. It's fine. So yes, you'll see why super high dimensions is exactly relevant in feature space for quantum classifiers. All right, so now I'm going to turn to quantum mechanics, and boom, I'm just popping it out there right away. So I'm going to give you a interpretation of quantum mechanics, which is at its heart, and that's basically, now it describes the behavior of electrons and particles at the atomic scale with extremely great precision. So you can think of it as nearly exact. And so this is the equation that, the central equation that describes the behavior of, let's say, electrons in a potential V. That's an energy potential. This includes atoms and semiconductors. Our computers are designed using this equation, for sure. And so, but here's the interpretation, and this is at the core of both what's strange and, well, what is strange about quantum mechanics? And a lot of other strange things emanate from this. But the way we interpret the electron's dynamics is that until it's measured, it moves as a probability wave. And I'll illustrate that very briefly in the next slide. But so this psi, when you solve this equation for whatever the potential is, then the probability of detecting the electron at position r at time t is given by taking the square amplitude of this function psi. And so, and this corresponds to the probability of measuring the electron at position r at time t. Any questions about this? So just kind of take this as the interpretation. And the more you think about it and understand it, the stranger it will be. That's the interesting thing about this. And here's kind of a taste of the strangeness to maybe make it a little more concrete. So, and I prefer to do this a different way, to really go through the cognitive dissonance of the two-slit experiment, but I don't have time, so I'm going to jump right to the interpretation. Again, an electron moves as a probability wave. This is what experiment is showing us, and it defies our logic. So let's say you kept shooting electrons out of a source one at a time, and you could even separate it, like each shot you could separate it by an hour. There's nothing important about how frequently the bullets or the electrons come out. Now, and then you shoot them through at this wall with two open slits. Now, you'd expect if the electrons just traveled classically, right, they would either hit the wall and not get there, or travel through the slit and make it to a detector at this second wall. You would expect classically this kind of pattern where you sum I1 plus I2 and get this overall kind of maybe hump, okay, at most a double hump. Instead, what you see is this interference pattern that would have come about if the each one individually moved like a water wave through two slits, could interfere with each other, creating, kind of high points and low points where there's constructive and destructive interference, and then finally was detected at the end. And when you do many, many experiments, this is the detection pattern that you keep finding again and again with experiment. And it's exactly described by solving this equation in this setting. Okay, so an electron moves as a probability wave, and that has further consequences. You constantly interpret kind of electron dynamics and state change probabilistically until it's measured, and then it is measured somewhere definitely, and that's kind of what's unusual. It moves as a probability wave. That probability when you calculate that probability, it tells you where and when your chance of detecting that electron in a given spot. So any questions? Okay,
Sure.
that's
the equation you've got here. That's a one-dimensional equation, right?
yeah, well, R can be a vector.
Oh, okay.
R is a vector, but yeah, and there's a gradient. So it can be three-dimensional, it can be any dimension you want.
Okay, that's great.
Any other questions? All right, so now why quantum? Okay, you could imagine, and people do call it wave mechanics, but why quantum? Okay, it comes from the fact that it's a wave, and this is just important to get into quickly. So because it's a wave, if I confine an electron, then let's say I confine it in walls. Well, for it to form a coherent standing wave, you have to have an integral number of wavelengths between these two walls for it to be a stable coherent wave. Similarly, if it's trapped in an atom, like this is what our atoms are like, with the nucleus in the center, you have to have an integer number of wavelengths that go around a given radius for it to be constructive interference, that it's a consistent pattern. So, but and it just turns out that the energy of the electron has to do with the, how fast the wiggles are. But just imagine now, if I wanted to increase the energy, I have to increase the wiggles in such a way that I get a new integer number, an n+1. Let's say I have n. Here I have 1, 2, 3, 4, 5, 6. To make it 7, I have to jump to 7 integer wavelengths, and that just creates a jump in energy. It's not continuous, and so hence the name quantum. It results in quantum energy states and other relevant measurable variables being quantized. Any question here? So that's why quantum. Now, how do we make use of this and there's a lot to say about quantum mechanics, which I'm not. It's a massive field, but I just want to give you a flavor for it because it's very relevant, obviously, to quantum computing. So how do we make use of this in a quantum computer? Okay, well, we're going to turn a bit, 0 and 1, into a qubit, into a quantum bit. And how do we do that? So physicists who do experiments can relatively easily, build resonators, quantum resonators. Okay, but when they do this in the easiest way, then the energies, these quantum energy spacings can be kind of equal. And that turns out to be a situation where you can't ideally control it. So instead, the current quantum computers, and this includes IBM's and Google's, are built with Josephson junctions. And I'm not going to get into what a Josephson junction is, but long story short, one of the ways of looking at it in the most simple way is that you can make it so that you've isolated 2 quantum states that you're going to be able to manipulate and control with electromagnetic fields, say, and they're nicely separated from the higher order state. There's still higher states, but they're nicely separated. If in this situation on the left, I wouldn't know which quantum state I'm in if I keep zapping it up to higher energy levels. I could get up to very high N, and then I don't really have like a perfectly controllable system. Here, I just want to control myself between, have control over the state 0, the lowest state, and state 1, the next excited state, and then have the other states separable, and I'm just not going to ever excite them. So is that clear? So at the end, I'm physically building these quantum qubits out of Josephson junctions to create a 2-state system that's robust and that I can control. All right. So how am I going to control it? All right. So here's a simple, one of the first gates, and then I'll introduce, and this is easy to do mathematically. You just write it down and I'll give you the interpretation. But to build this with actual hardware, this just H operation is actually some electromagnetic pulse that you give to this Josephson junction resonator system, and you take the lowest energy state, the zero qubit, and you can put it in a superposition state. So this is yet another, this is one of those consequences of quantum mechanics. This is a trivial property of the Schrödinger equation that you can have. If 0 is a solution and 1 is a solution, then the sum is a solution, the superposition. But in terms of interpretation, what we've done is by zapping it, and with this Hadamard gate, what we've done is we've put it in the state 0 or the state 1 with probability 1/2. Remember, I said probabilities come from squaring the amplitudes. And so that's the rule. And so when I square the 1 over square root of 2, I get 1/2. So I've put the 0 state in a state such that it's either in state 0 or 1 or both with probability of 1/2. Okay? And that's what the Hadamard gate does, and that's the interpretation of superposition at the same time. Now, what the Hadamard gate does to the qubit state in 1 is it creates a superposition, but with a minus sign. And this has differences, even though still the probability of measuring state 0 and state 1 is 1/2. This behaves differently than the above state. Okay? Any questions? All right. So now I'm going to go to an arbitrary superposition. I'm not forced to just put states in either state 0 with probability 1/2 or state 1 probability 1/2. It turns out that there are gates, rotation gates, they can dial in an arbitrary probability of coefficient alpha in front of state 0 and beta in front of state 1, but the probabilities have to sum to 1. My probability of measuring state 0 or state 1 has to be 1. And so that's why alpha squared plus beta squared has to equal 1. All right. Now, and then measurement in quantum mechanics is extremely important and formalized. And so one way of now looking at how to think about and begin to kind of develop a notation and quantify the probability of measuring the qubit state in 0 is it turns out that the states satisfy these beautiful orthogonality principles. So the state 0 and 1 are perpendicular to each other, and I can write this notation is a quantum way of writing an inner product and a state. And so the inner product of 0 and 1 is 0, and 1 and 0 is 0. And these individual states are normalized. So you can think of these as orthonormal vectors. So 0, the inner product of 0 with itself is 1, and 1 with itself is 1. So when I measure the probability in state 0, a formal way of doing that mathematically is taking the inner product of the full state psi with 0 and calculating the square amplitude, like I said. So since 0 and 1, 0 is perpendicular to 1, I get 0 for that. But 0 and 0 is 1. And then I take the square of that, and that's alpha squared. And that's what gives me the alpha squared probability for measuring the psi, a state that's the state psi in state 0. And then similarly, going through the same logic, I can measure the probability of the qubit being in state 1, and that gives me beta squared, following the same logic. Okay, any questions? I'm throwing a lot at you. This is really a lot of the quantum principles all at once and quantum mechanics. Okay, so are we stuck with 1 qubit though? No. Okay, so here is a major gate that's been implemented on the IBM system, and others have implemented it. And this is just using like a logic theory, but they've implemented it in hardware. But this is a controlled knot. And so let's say I have 2 qubits now. Traveling down 2 lines, okay? So I have the X qubit and the Y qubit, and let's say the X qubit is in state 0. Then if it's in state 0, the state of Y just passes on to the end as is. So here the input is 0 for X, and Y is 0, Y remains 0, okay? When X is 0, and y is 1, y remains 1. Okay, but now let's say x is 1. That now flips the qubit y state. So let's say x is 1, then if y is 0, then it gets flipped to 1. And conversely, when the qubit x is 1, the y qubit state gets flipped from 1 to 0. Okay, so it's a controlled knot. There's a knot on the y, but it's controlled by the x. Any questions? All right, so can we do anything interesting even with these two gates? And you can kind of see what a quantum circuit starts to look like. In fact, we can do something extremely cool with just these two gates. We can build an entangled state, which I'll describe in a second. And its importance in a second. So let's say now I start out with 2 qubits in the 0 state. Okay. Now, and I designate the state, the quantum states before and after each gate operation with these psi vectors. Okay, so at psi 0, it's 0, 0, and this is another way of writing a 2 qubit state. Okay, and then so I take the first line through the Hadamard gate, so that if you recall, when it's 0, will give me 1 over square root of 2, the 0 plus the 1. The second qubit was not operated on. Okay, now I take the psi 1 state through a CNOT gate. So when the first qubit is 0, it passes on as 0, the second qubit. But when the second one is 1, it flips the second qubit to the 1 state. So now I have this state right here, okay, which maybe looks innocuous to you. This psi 2 equals 1 over square root of 2, 0, 0 plus 1, 1. But now if you think about it, it means these 2 qubits are perfectly locked into place. If I measure the first one as 0, the second one is 0 for sure. If I measure the second one as 1, the second one is 1 for sure. Okay, and this is an entangled state. They're locked into each other. And actually, and I won't go into this too long, but this is where Einstein actually thought he got quantum mechanics. This turns out like this state is another simple consequence of Schrödinger's equation. In fact, a kind of a trivial one. It's like following differential equation theory. Once once you've written that equation down, Schrödinger's equation. But so then Einstein imagined, all right, let's say I developed a state and then I separate the 2 qubits by miles. He thought this experiment would fail, or even if they're just a little far apart, they're not going to be perfectly locked in place. And they have been. People have done this experiment gazillions of times, and it's turned out to be true. And in fact, one group from China got a science paper. They beamed entangled photonic qubits from a satellite to 2 distances that were far apart on Earth, miles and miles. I can't remember now if it's hundreds or thousands or whatever. It was a huge distance, and they got entanglement, and they got a science paper out of it. So it's a spectacular effect, and people keep pushing the envelope on measuring entanglement in distance and in the size of the quantum systems that they're studying. Any question?
Yeah, so I've always been confused with this because I've heard different things. So when you have entangled states that are separated by a distance and you change one of them so that the other will change, is that change, does the other one change based on like a speed of light causality moving from one to the other?
So, okay, so that's a great question. I'll try to answer it briefly. So first, remember, and it's critical, the language, because it helps your understanding. There's no change. It's just you measure a particular state, right? It collapses. So the state of the system before the measurement is really this 1/2 probability of measuring 0, 0 and 1/2 measuring 1, 1, even if those 2 qubits are separated by miles, right? Now, here's the thing. So the information not traveling faster than the speed of light is not violated because I can't send an encoded message. It turns out the collapse you can view as instantaneous, but But so just say, let's say I have Bob and Alice separated by miles, right? And Bob measures 0 and Alice measures 0. They can't communicate to each other what they found. You see, they just both know that they got 0. And let's say I did a series of experiments. I generated entangled states and I did these measurements again and again and again. So then I'd have some set of 0s and 1s, and Bob's and Alice's 0s and 1s would be perfectly in alignment. But they would either have to send a message at the speed of light saying, here's my encoded message. And then they would both say, wow, it's perfect, entanglement works. But it would have taken a message to get there at the speed of light. We can go into this more if you'd like, but that's the essence of why it doesn't violate the speed of light information kind of maxim, if you will. Does that answer the question?
A little bit, but so is it possible to change one of them and then the other change, or does that just break the entanglement?
Well, it's if you measure, okay, yeah, I see. If you measure one, the other one is measured. It's in that state. So yeah, so if they're separated, if I measure one and I get 0, the other one is 0. If I measure 1 and I get 1, the other one is 1.
Oh, I guess I'm asking is there any method known where you can force it to change state?
Oh, you mean like, well, not if I prepared it in this state. There's only one other complication that has to do with noise. It just turns out that, so you have to maintain what's known as a coherent state, this quantum coherent state. Obviously, the system is more complicated when you add in environmental variables, which then create a more complicated quantum state, and they can mess things up and create error. But if you've really isolated the environment and you've created this perfectly entangled state, it will be perfectly correlated. There's no way you'd have to do something. You'd have to once again operate on like one of the 0s or the 1s and flip the state to change it. But then you wouldn't have. But then you don't have this entangled state anymore.
Yeah. Okay, that's what I was at. I understand.
Yeah. You know it. Once you've created this entangled state, that's that. It's locked in. All right. For the sake of time, I'm going to move to the next. So, what is quantum machine learning? That's what I'm here to talk about. And what's the nature of the quantum speedup? And I'll just give you the intuition. And here's a famous review by Seth Lloyd. He's kind of the grandfather and giant in this field of quantum machine learning. And this is a review of some quantum speedups. And I would say a lot of this summarizes the literature, especially the literature that has to do with assuming basically that you have a universal powerful quantum computer that can do a lot, and that you can get a speed up if you had such an instrument. But it doesn't necessarily summarize the result of papers where they take it through an actual quantum computer or they use gates. And so there are some assumptions made about the hardware that don't exist right now, but still there have been proven speed ups. And what's the intuition for why this could be powerful? Well, I've kind of told you 2 qubit states. I've described them. And if you think about it, 2 qubits encode 4 states, 0, 0, 0, 1, 1, 0, 1, 1. So if you kind of go through the thinking of this kind of digital thinking in quantum space, 3 qubits corresponds to 8 states, 4 qubits to 16 states. Generally, as I run down this, n qubits corresponds to 2 to the n states. I mentioned kind of genomics, which is of interest to us, and there's basically 3 times 10 to the 9 billion letters in the human genome, and so 32 you can operate on 32 qubits as opposed to 10 to the 9 kind of states directly, and execute operations on 32. So you can see that even with a 32 qubit quantum computer, you might be able to do some very powerful things in genomics, and we're getting there. So the idea is that you can explore an extremely rich state space, an exponentially powerful state space with, in principle, a low number of operations in that state space. And I'll show you how our quantum classifier executes a speed up of this basic algorithm by operating in this state space. Any questions about this? And then we were talking about this before the lecture all started. It turns out Shor came up with a famous algorithm that basically shows that you'll break the internet encryption, our current encryption scheme, if you had a powerful universal quantum computer. There's a specification for how powerful and all that. I'm not going to go into that, but this is one of the reasons actually nations are kind of in a race to develop a powerful quantum computer. So let me come back to our classifier now, more concretely, and now I'm going to start getting into the quantum version of our classifier. So similar to the as I described for the classical one, I'm going to encode the regions using a binary scheme, but now you can see why. I'm putting them into qubit states. So here for 8 regions, I have 3 qubits, and it's the same digital encoding effectively, okay? And then now the way I encode my control and my disease vectors, if you will, is I multiply the qubits by whether, you know, they have that genetic aberration or not. So in region 1, I multiply this qubit state by 1. And in this case, the control had it. It's the same example as before. Now here, disease doesn't have it, so I'm going to multiply that by 0. And so here is the final control state where I have the disease vector, and it turns out I'm also going to encode the class state, which for control was 1. And so here, and the states have to be normalized. Quantum mechanics demands it. So the full state is normalized, so the probability of measuring the any one of these outcomes is one, the sum of all the probabilities. And you can see here, I had a 1, 1, 1, 1 in all first 4, and that's what these first 4 qubit states are, but I don't have any of these last 4 in this state because they're all been multiplied by 0. And then of course I have the class qubit as 1. And then the disease state is very similar. It's just now these last 4 where you can see 1, 0, 0, 1, 0, 1, etc. The class qubit is 0. And this is now how I'm coding the control and the disease state. And then similarly, the test state is you can see I have the 0, 0, 0. That's multiplied by 1. And then I have to jump all the way to the 1, 0, 0 before I see another 1, and so on. And that's the test state. So that's how I'm going to encode the disease and control and the test vectors in my quantum computer. Any questions? Okay, so we're getting very close now to how the classifier works. So now I just have to calculate an inner product, and I can't do that with the regular operations of a classical computer. So first, I'm going to just very briefly point out the actual encoded states that we use. I'm not going to go into great detail about this. I'm just going to point out, now this is where it starts to sound a little silly too. I'm chopping the genome up into 2 big regions. So it's not really a genomic classifier really, but it was the way we were thinking. So this is for the 5 qubit. Remember, now I'm 5 qubits, and I'm taking up some qubits with a class qubit. I'll show you taking it up another qubit with another one. So I'm not left with many qubits. So I can only encode 2 regions here. And so the disease class vector, I have an aberration in the 2nd region. For the normal class vector, I have aberrations in both. And so, and my test sample is in the 1st region. And if you just look at it, that means my test is going to be the control class, or the normal, quote unquote, if the classifier works. It's not going to be disease. And then similarly for the 16 qubit quantum computer, my disease vector is 1s up to the 32nd region, and then 0s, and then my normal is easily classifiable. That is all 0s up to the 32nd, and then 1s from 33 to 64. 4. And then my test sample is 1s up to the 16th and then 0 beyond. So once again, I'll just run through this quickly. The test should be disease in this case. And I'm not going to go into the detailed annotation of this. And then this was for another application that I'm not going to describe. So that's just the encoding of the actual states we started with, okay? And this is obviously toy data. This is not real data. So how do I execute the inner product? So the way you execute the inner product is by doing a swap test. And I'll describe the swap test next. But to describe the swap test, I have to tell you about the C-swap gate or the Fredkin gate. Okay, and that's kind of similar to the CNOT gate in a way. So now I have a swapper qubit, okay? And when it's set to 0, all right, and it passes right along, the states get passed right along. These can be 0s or 1s or states in arbitrary superposition. Okay, so phi goes to phi, psi goes to psi. But if my swapper qubit is 1, then I swap the states. So if you look carefully, the phi goes to psi and the psi goes to phi. So I've swapped them, okay? Any questions? All right. So this is busy, but I'll take you through it in a few steps. So this is now, and let me maybe get to the punchline first. What this circuit does, it's a Hadamard, a Fredkin gate, Hadamard, and a measurement. And I'm going to measure the swapper qubit in the state 1. What's the probability of measuring it in state 1? That's it. That's the measurement. And what that ends up giving me is the inner product between the state phi and psi. And if you think about it, that's kind of getting me where I want to go. I'm building an inner product classifier. So this actually executes the inner product. So I'll just take you through a few steps so you have a concrete feel for it. None of it, it's just details now with what I've told you. So here I've labeled the state psi1, psi2, psi3 before and after relevant gate operations, and then measuring the probability of the swapper qubit in state 1. So I start out with psi1 in state 0, phi, psi, okay? And then I apply a Hadamard gate, and then psi2 is just that 0 gets turned, if you remember, into 1 over square root of 2, 0 plus 1. That's all that happened. Phi and psi are the same, okay? And then after the swapper operation, the first state is, the first part of the state has a 0 qubit in the first line, so the states pass along as is. Phi and psi get passed along as is. But the second qubit was in state 1, and so they get swapped. So physically, these qubit lines now, this qubit is phi state, and this qubit is psi. So the order matters, okay? And the state is still normalized. And then after the Hadamard does its usual thing. For the 0, it turns that into 0 plus 1 over square root of 2. And when it's a 1, it's 1 minus 0 over square root of 2. I can collect terms algebraically, that's allowed. And so when the smoke settles, when the dust settles, this psi4 state can be written as kind of having the swapper qubit 0 with this state and the swapper qubit 1 with this state. Now it just turns out if you follow the instructions I gave you before on what a measurement means, it means I project the swapper qubit into state 1. I look for the inner product between 1 and this big fat psi4 state, and that's going to be perpendicular to the 0, so that gets wiped out completely. And then I take the magnitude squared. That's just the inner product of this state vector with itself. And when I just do that, that's actually not very hard really to do. I'm showing you actually all the algebra. You end up with this result, that the probability of measuring the swapper qubit in state 1 is 1 minus this inner product between phi and psi squared divided by 2. 1 minus this inner product squared divided by 2. Any questions? Okay, so now I can actually tell you what our actual, the schematic of what our algorithm is, our quantum algorithm. So we have a class qubit, we have the train qubits, D1 through Dn, and we have the test qubits, T1 through Tn, and we have the swapper. Okay, now we don't just execute one swap, we execute n swaps. And what do we swap? And I'll show you more concretely in the next slide, explicitly, but in words, we swap the most significant digital kind of encoding qubit, Dn and Tn, we swap them. We swap Dn minus 1 and Tn minus 1. We swap Dn minus 2 and Tn minus 2 all the way down to D1 and T1. When you do the algebra, this ends up swapping the train vectors or states and the test. Okay, we then take it through an effective big fat swap operation and a measurement, and we end up getting the inner product between the train and the test. We also have the class qubit label. So what we measure, I'm showing you two measurements. We measure the class label and we measure the swapper label. And then we just look for the inner product that's greater. And that's how the classifier works, okay? And this is, you guys know this from your machine learning. I pretty much described this, pretty much the simplest classifier you could imagine, a dot product based kernel linear classifier. It's as simple as it gets and approaching the least powerful as well, I'll be honest. So by that logic, this is about as simple the simplest quantum genomic classifier you could build. But here's what's interesting. Now, it's almost like magic. I'm only performing n qubit, little n qubit operations to calculate this inner product. That's log n in the number of features. Remember, my dot product, I normally have to do order n operations. So if it's the genome, I have to calculate an inner product between feature vectors using 32, 3 times 10 to the 9, 3 billion operations. Here, I only have to do 32. So, and the bigger the feature vector, the better, right? The greater the speed up. So it's an exponential speed up. And I'll get into a thorny issue of preparing the states at the very end. But I want to point out that for the 5-qubit system, we can actually prepare an arbitrary state. I won't go into the details, but it doesn't have to just be like I said, like a 1 and a 1, 1 over square root of 2, 1 over square root of 2, where they're equally probable between like say the two regions. I can actually dial up an arbitrary value between the regions, and I do so, and I'll get into that later. Any questions?
Yes.
Go ahead.
Question. So just to clarify, what you're doing here on this schematic is you're comparing one vector to another vector.
Correct.
And so later, would there be ways to build up a set of vectors that would represent a single class, or?
Yeah. Well, so okay. No, and I think you're getting into, yeah, no, I see what you're saying. So remember, this is excellent. This is actually an excellent question, a really good point to bring up. So remember, I said that I sum all in the way that I casted the classical classifier formally, that I pre-sum all the samples. Yeah. And for disease and control. So the reason we even thought of it that way is because this would be a hybrid classical quantum classifier. We would pre-sum all the class vectors first, even if it's thousands of samples, and then execute the classifier on those pre-summed class vectors. The reason is you'd have to come up, and I'm sure someone's done it. If you Google anything with quantum, you find some algorithm. just figuring out how to sum values of coefficients is non-trivial. You have to find an algorithm to do it. But this is one way to very efficiently, like you pre-sum it classically, but then get the exponential gain by calculating the inner product using a quantum classifier. Does that answer the question?
That does answer my question. And I have another question too.
Sure.
Maybe this is just me being less familiar with quantum computing, but I had the impression before that sometimes in a quantum computing operation, you have to repeat it multiple times because there's a certain amount of quantum randomness that still happens.
That is completely true.
Okay.
So if you think of, yes, so let me, so let me go to the next slide and I get into that.
Oh, okay, sorry.
No, that's exactly right. So and that's a good point. You have to measure. So remember, I've measured the probability of being in a state. To get statistics on that value, on that coefficient, I have to do it thousands of times to build up that probability value, that estimate correctly. I have to sample it many times, so that's correct.
Oh, okay. I didn't realize I was getting into your next slide though, so let me just.
No. It's fantastic. It's an excellent question. So Does everyone understand? That is exactly the point. So, and IBM has set it up. Anybody who sets up a quantum computer, you don't just get one measurement. They instantly just do thousands once you set up a circuit. They do it many, many times. So you get the statistics on your probability of measurement. That's excellent. All right, so here is kind of a little bit more of the mathematical formalism. I'll just walk you through it briefly. So it's saying the same thing. So my full state is the disease state where I have 0 class qubit. I have my disease pre-summed encoded vector. I have the test vector, and I have the swapper qubit set in the 0 state. And similarly, I have control, class 1 qubit, the full D1, the full control state at the same test vector, 0 swapper qubit, and it's normalized. So then I encode, this is just the formal look of the multi-qubit encoded binary encoding train feature state and the full test feature state. And as I mentioned before, I execute swaps between the DN and TN, DN minus 1, TN minus 1, etc., down to D1 and T1. This ends up swapping the big fat DI and T. And then when I execute the full swap test operation on this multi-qubit state, I end up getting this probability theoretically that so the swapper I'm measuring in state 1, that's what this first one is. And then the I is the class label, 0 or 1. And you can see it's 1 minus the inner product. So, and I want the bigger inner product will develop the class, so it's the smaller row. So row 1, 0 less than row 1, 1 corresponds to the test being disease, and then vice versa. And I execute this thousands of times to get statistics on row and get the appropriate values, which I think addresses your question, Jonathan. That's exactly right. So any questions here? So I'm getting very close now to the end and showing you performance. So, so first, here is just you don't just have a C-swap gate. I was showing you real gates that are available on the IBM Q system, meaning the Hadamard and the CNOT. You have to use 18 gates, including 1, 2, 3, 4, 5, 6, 7, 8 CNOT gates, and I'll get into why that's an issue. But you have to execute these 18 gates, which I'm not going to get into at all, to execute the actual swap operation. Okay, so a little complicated. And so this is our circuit. And this is, so the top circuit is the most intuitive version of the circuit that my postdoc, Kunal Katharia, he formulated a lot of this and executed it. He did a great job. Here's the swapper, the test, the train, and the class qubits, and here measurements. Okay, so and this is what the most intuitive way of putting the circuit together. you have to reconfigure it because not all these lines are connected to each other. So there's a connectivity constraint on the actual IBM hardware. So you can think of this is what we used for simulation, and this is what we used on the actual IBM system. So, and then we empirically found that measuring the swapper qubit in the state 1 worked the best. So I'm going to ignore the bottom 2 values. And so this is simulation now. This is close to what exact should be. And you can see that we get this result, 1, 1, 1, 0. Take my word for it now. So this is the control state, and this is the disease state. This is lower. So a lower row means it should be control, and that turns out to be the correct state. So it classified it correctly. But if you look at this is the simulation. This is the actual quantum computer, and it's not quite right, but it's actually not bad. And I'll show you a sweep over a whole range of values to show you that it actually isn't too bad for a 5 qubit. So this is now the actual quantum computer for the swapper one and the normal or control class qubit measurement, and then for the swapper qubit 1 and the disease or 0 a class label measurement. And you can see they're close to each other, and the ratio is not bad actually. So this is the 14 qubit, and this is just the one that was the most intuitive to draw. And so I should point out too, this 5 qubit only involved 1 Fredkin gate. Okay, that's critical. This one involved 2. We allowed 2. In principle, we could have used more to swap more states, but we built states that you only had to swap 2. But even with 2 Fredkin gates, this failed miserably. So if you just look simply at the 1, 1 of simulation and 1, 0, this is what is near exact ideal. And look at the actual. It's way off. It misclassifies it. The ratio's wrong, and I'll illustrate that more clearly in the next slide. So this is now a full sweep of the performance of the 5 qubit over like a measure of classifiability. So simply, we came up with this simple metric of classifiability. That's the difference in the inner product between the test and the normal minus the test and the disease, taking the absolute value. And very intuitively and simply, if the data is perfectly classifiable, like the test is exactly equal to the control, and the control and the disease are perpendicular, then you get it'll perfectly classify. You'll get the inner product between test and control being 1 and the other one being 0. So F is 1. That's perfectly classifiable. Similarly for the disease, if you just flip the cases, if T is exactly equal to disease, but completely perpendicular to control, you'll get F equals 1. And perfectly unclassifiable is if the test is equidistant between disease and train. That means this kind of classifier will fail. It can't classify that kind of data. And we actually use those rotation gates to create a whole range of classifiability all the way from 0 to 1. And if you look now, the 5 qubit theory, that's our actual, the theoretical 1 minus the inner product squared theoretical result for the rho 1, 1 divided by rho 1, 0. That's this kind of pinkish one. And that's what that curve is. The 5 qubit simulator is going to be very close. It's just sampling the true. If we sampled it infinitely many times, meaning we made infinitely many measurements, they would be right on top of each other. But there's a little bit of error even in the simulation. That's just sampling error. Okay, and then now this curve, which is kind of greenish, that's the actual IBM 5 qubit quantum computer. It's not perfect by any stretch, but it's not horrible. This is it's a pretty complicated circuit, right? It's this thing. So not bad, that's at least in my view. but the 14 qubit is just completely wrong. So the theory is shown in green. That's just a perfect 2.0. The simulator with a little sampling error is near it, but the actual is misclassifying and way off. Okay, so and then I'm just showing you, this is the CNOT, the 2 qubit or CNOT connectivity constraints. Not all gates. These are all like the 0 qubit gate, the 1 qubit, the first qubit gate, the second, the third, the fourth for a 5 qubit quantum computer. Not every line is connected to every other one. This is the constraint. You have to put your CNOTs in this, like 1 has to be pointing to 0, 2 has to be pointing to 0. So you have to redesign it after your first intuitive design, which is just a pain in the, you know what. And this is similar for the 14 qubit quantum computer. This is the constraints you have to live with. So let me just end. This is a busy slide, but let me just end with conclusions, challenges, and opportunities. So quantum computers are still, they're in their noisy early state. And so believe it or not, even maintaining this kind of spooky probabilistic quantum state is now, that's desirable, and that can be messed up by the environment. You can think of it as quantum states from the environment now mixing in, and then effectively even creating a self-measurement of the system and destroying the beautiful quantum kind of that state that you're trying to operate on. So that just pops it into a measured state at a time when you don't want it to happen. Gate fidelities are limited. Like, let's concretely, with the Hadamard I showed you, it's supposed to take the 0 into 1 over square root of 2 of 0 plus 1. Well, it doesn't exactly give you 1 over square root of 2. It's a little off. Okay, so, and the CNOT gates actually have pretty serious fidelity issues. So that's when you operate on 2 qubits. So the more CNOT you have, the more likely you're not going to get the result you want. And that's probably why our 14 qubit with two Fredkin gates and 16 CNOTs fails, at least 16 CNOTs. Okay, it turns out, like, this is a kicker now. Inputting data into a quantum computer is a challenge. So that can, unfortunately, depending on the nature of your data, the actual coefficients, it can take an exponential number of gates to input the data. And I'll show you ways that I'm thinking of getting around this, but this is actually one of the challenges. It's one of those things that when you first encounter it, you can't believe it. But if anyone tells you getting classical data into a quantum computer is a challenge, the way to think of it is you have to execute those gate operations to get whatever number you want in front of your state. Well, it turns out that first can be actually hard to figure out. And second, it can actually destroy your advantage because it can take an exponential number in the number of qubits, number of gates to actually get that number in place. So that's an actually known hard problem in the field. But nevertheless, we were able to develop a near-term kernel-based quantum classifier, which leads to an exponential speed up in classifying the inner product. So if we were working on giant state vectors like on the genome, we could do this. We could calculate inner products with 32 operations as opposed to 3 billion. And we also developed an n-qubit swap operation, which is relatively novel. We executed this on 5 qubit and quantum classifier, and we found that the performance was reasonably good with 1 Fredkin gate composed of 18 IBM native gates, but it failed miserably with 2 Fredkin gates. So that's kind of one gross measure of where we were, and this was a little over a year ago. And then finally, to end on a hopeful note, one of the ways around some of these challenges is to actually encode the data in a very quantum way. I showed you that these things you can actually encode things in angles instead of directly as the coefficients as being the numbers in front of the states. And that might allow for just natural quantum operations to encode the data with low gate depth, so maintain the advantage of the circuit, but also it's a way to generate complex decision boundaries. And as I was thinking about this kind of thing, papers are coming out, including by Seth Lloyd. He's got one on the archive right now, exactly with this idea, that you can generate very complex decision boundaries and then use swap operations to generate more complex kernel-based classification. So with that, I'll end, and I'm going to give a big shout out to Kunal Katharia, who, together with me, I came up with some of the general ideas for where we should go. We worked off of a powerful paper by another group, but Kunal put a lot of, he conceptualized a lot of this, and he did all the circuitry and development of the theories. So I did some of it, but he did most of it. So I want to give him a big shout out. This was actually funded by the NIH, but don't get too excited. You folks that like to apply to them, they're not funding this anytime soon. This was out of a supplement of a UO1. And with that, I'll take any further questions. Thank you.
Well, I gotta tell you, I think this is absolutely fantastic and fascinating. And I did have a question though, and I think this is a pretty generic question that I hope will benefit for everybody. If those of us in the audience would like to learn more about quantum algorithms and learn a bit more of the math that you're using, where would you direct us? And are there some good introductory books or introductory papers? And also, if there's any places we should quantum computing.
I'll put this in the chat maybe. This is the classic, but there are others. And so maybe what I'll do is maybe I'll put in a couple. Maybe I'll send them to Jennifer. Jennifer, is that okay if you're here?
Jennifer had to leave at 4. She wanted me to pass along a thank you, but you can send those to her as well. I'll let her know.
Okay, so I'll do that. I'll send out some resources. I'm still, we jumped into this game, and because of my physics background, I was able to jump in kind of quickly, but I still want to go through this. And anybody, I'll tell you too, I'll be honest, I don't have any resources right now, and I may get them in November through this, working possibly with pharmaceutical companies, believe it or not. But anybody, if you guys are interested in this, we can start working together. I'd be happy to do that. I really would, because to be brutally honest, I'm doing this out of love. I think if you can tell, I never fell out of love with quantum mechanics. And so the ability to apply this to different areas. So I'll share those books and resources, classic ones that I've encountered, some papers. You can tell me kind of maybe areas of interest you guys have. And then I would love, even, knock on wood, I hope this AI Institute gets funded. If it does, here's the dramatic thing for all of us. This is maybe relationships for life. I mean, this is going to start a powerful set of collaborations between us, students, faculty, and otherwise, right? And but I would love to get this going. If anybody's interested, let me know, because I'm passionate about this.
Well, that's awesome. I'll tell you what, I'm really interested to see what kinds of things the quantum computers can do for machine learning. And that kind of gets me to my second question, which is a bit more from my own personal curiosity. You've made a linear classifier now on a quantum computer. That's really exciting. Have you thought about wanting to take it up to more complicated classifiers, or are you waiting for the hardware to catch up?
No. So and I'll send you this paper. I think you'll be interested in this, and I still have to read it, frankly. There are a couple of papers actually that address this to some extent. So no, I'm interested in more complex classifiers. And as I was thinking about this, I was thinking about the data input problem because it's thorny. And so then I thought, well, wait a minute, we're thinking in the box a little too much, that we just put the actual, like we sum the class state vectors, and we put, like, let's say I find in 5, in a given genomic region, I find 5 aberrations. I put the number 5 in front of the state. Well, that's thinking too much in the box. It turns out if I do it with some kind of complex encoding that's just very quantum-like and very associated with the gate operations, I might limit that. But it turns out simultaneously, if you come up with non-trivial encodings, you can actually create non-trivial decision boundaries. Mm-hmm. So you can create highly nonlinear decision boundaries. So now a nonlinear kernel classifier. So Seth Lloyd just published a paper on that. Well, published. He sent it out to the archive, but Seth Lloyd being Seth Lloyd, you know, that archive starts to get citations way before it's published. But yeah, so I'll send you that, but I'm very interested in going in that direction. And then there are people that have, so if you Google, I guarantee you this, Google your favorite kind of AI or classifier or anything and put quantum computing or whatever next to it, you will find a paper. Now, what I will say is, so the field is moving fast, but what I'll say is a lot of people write theoretical papers where they're just doing very theoretical unitary transformations and showing speed up, but not necessarily like making it so that they can implement or even simulate the algorithm, right? Because maybe they've made an assumption that you just can't right now in any way make up in hardware or even simulation. Okay, but I would say there are people beginning to concretely think about even deep learning and other areas. And so there are plenty of algorithms out there. And then what I'm trying to convey to you is there's a spectrum in the style of papers going all the way to just theoretically, you can do it with these unitary transformations and this encoding, but it's nowhere close to even being something you could try on even a simulator, to something that's got gates and is somewhat concrete. So that's just, it's almost like a warning. You'll find lots of quantum machine learning papers, but then there's this spectrum. So depending on your interest, and I imagine you'd like something that's close to implementation maybe.
We're very interested in, my personal research is about computer vision, especially as applied to radiology. So that's much more close to implementation, yes.
I bet you there's papers on that. I'd be shocked if there's not. Everything I Google, I find there's something, but then it's a question of how theoretical or how concrete it is.
Okay. Well, thank you so much for this wonderful talk. I've really enjoyed it. Thank you for indulging my questions. I know I've had a lot.
Fantastic questions. Thank you. I appreciate it, Jonathan.
Thank you.
You bet.
Yeah. Thanks again, Stefan. It's a great seminar. Also stimulated very interesting, very good questions. We really appreciate you give us the seminar to our AI campus side.
I really appreciate the opportunity. I appreciate the invite, and this was a pleasure. This was a pleasure, and I hope we continue to work together for a long time.
Yes. Yeah. Okay. Yeah. Thanks again, and Jake. I think we will end here.